Okay, hi. Today we will have some examples illustrating how we can evaluate integrals of algebraic functions. For the objective of this lesson, at the end of the lesson, you should be able to evaluate integrals involving algebraic functions using the basic integration theorems or the chain rule. Okay, let us first have a recall of the different properties of indefinite integrals and the basic integration formula. And for number 1, we have the integral of dx is equal to x plus c, or in general, the integral of du for any function u is equal to u plus c. This is based on the definition of an integral. For number 2, the integral of a constant c times function f of x dx is said to equal c times the integral of f of x dx and is equal to c times the antiderivative capital F of x plus c. If we are evaluating the integral of a sum or difference of functions, then this is equal to the sum or the difference of the integrals of each of the functions. And for the integral of x to the n dx, for any n a real number not equal to -1, the integral is said to equal x to the n plus 1 divided by n plus 1 plus c. Okay, this is the power formula for integration. And working with the more general form, the integral of u to the n du for any function u is equal to u to the n plus 1 divided by n plus 1 plus c. Again, n is a real number not to equal -1. So to illustrate, consider evaluating the integral of 6x squared minus 4x plus 5 dx. For this integral, we will be applying the rule to evaluate the integral of the sum or difference of functions, and that the integral of 6x squared minus 4x plus 5 dx can be expressed equal to 6 times the integral of x squared dx minus 4 times the integral of x dx plus 5 the integral of dx. And in evaluating the integral of x squared dx, we make use of the power rule, and this would just result to having an x cubed over 3. Hence, for the first term, we will have 6 times x cubed divided by 3. For the second term, the integral will be given by -4 times x squared divided by 2. And then we have 5x for the third term, and we have now to add the arbitrary constant c. Or simplifying this expression, we have 2x cubed minus 2x squared plus 5x plus c. For our second example, let us evaluate the integral of 4 the square root of t plus 2 over the square root of t dt. Now, the variable of integration can be any variable. In this case, we have this variable given by t. Now, to evaluate the said integral, let us first transform 4 the square root of t into 4 times t to the 1/2 and 2 divided by the square root of t in terms of 2 over t to the 1/2, or we can write it as 2 times t to the -1/2. Hence, the integral of 4 the square root of t plus 2 divided by the square root of t dt can be written in this manner. We have 4 the integral of t to the 1/2 dt plus 2 times the integral of t to the -1/2 dt. And in evaluating these integrals, we will be using the power rule. Hence, for the integral of t to the 1/2 dt, we will have that equal to t to the 3/2 divided by 3/2. Again, using the power rule. And for the integral of t to the -1/2 dt, we will have t to the 1/2. 1/2 is from -1/2 plus 1. So the exponent will now be a 1/2, and we need to divide this expression by the exponent 1/2. Hence, the integral now can be written equal to 4 times t to the 3 halves divided by 3 halves plus 2 times t to the 1 half divided by 1 half plus the arbitrary constant c. But 4 divided by 3 halves is equal to 8 over 3. And 2 divided by 1 half is equal to 4. Hence, this integral is now written equal to 8/3 of t to the 3 halves plus 4 times t to the 1 half plus c. Okay, in this particular example, we will show three solutions, three different ways of evaluating the integral of 3x plus 1 squared dx. Okay, so the first solution is done by first expanding on the square of 3x plus 1. And that will give us 9x squared plus 6x plus 1. So that the integral of the square of 3x plus 1 dx is evaluated in terms of the integral of 9x squared plus 6x plus 1 dx. And if we are going to evaluate the integral term by term, then this would result to having a 9 integral of x squared dx plus 6 the integral of x dx plus the integral of dx. Okay, and evaluating the integral of x squared dx by the power rule, this will just give us x cubed over 3. Okay, and the integral of x dx also done by the power rule would result to an x squared over 2, and the integral of dx is just an x, and therefore we come up with 9 times x cubed over 3 plus 6 times x squared divided by 2 plus x plus the arbitrary constant term c. Or simplify on this expression, we have 3x cubed plus 3x squared plus x plus c. Now, the second solution presented here is done by fitting the integral to the form the integral of u to the n du, so that we evaluate the integral using the more general form of the power formula. So, in this particular form of the integral of 3x plus 1 squared dx, if we will fit on the expression 3x plus 1 squared as our u to the n factor, then n will be 2 and u would be 3x plus 1. And with u equal to 3x plus 1, du would equal 3 dx. So if you will go back to this given form, we do not have exactly the required form of u to the n du, because for du we lack the constant factor 3. So that if we are going to correct the form so that we will see exactly a u to the n du, then we need to have that 3 factor with the x. So if we are going to introduce that factor 3 in the integral, then we should multiply the whole integral with the reciprocal of the said factor, and that is equal to 1/3. Now, why do we have to do this? It's because we do not want to change the identity of the expression or the integral, and that what we have introduced here really is just a factor equal to 1, as given by 3 divided by 1/3. So if you have done this process, then the integral of 3x plus 1 squared times 3 dx exactly would fit the required form of u to the n du, where u is 3x plus 1. And so we now can evaluate this integral using the power form. And so we have that integral equal to 3x plus 1 cubed divided by 3. And that the integral, the whole thing, would equal 1/3, this factor 1/3, times 3x plus 1 cubed over 3 plus c. Or we can write this as a 1/9 of the cube of 3x plus 1 plus c. Again, please take note of what is stated here. A constant factor can be introduced into the integrand provided its reciprocal is written before the integral sign. Okay, so that is solution 2. Now, for solution number 3, what we're going to do is to make use of a u substitution so that the given integral can be shown and can be written as a new integral in terms of the variable u. So here, for the integral of 3x plus 1 squared dx, again we choose 3x plus 1, the base, to be our u, and n is 2. And with u equal to 3x plus 1, du would be equal to 3 dx. And from there, you can now express dx in terms of u as given by du divided by 3. So that this integral here can now be written as equal to the integral of 3x plus 1, which is our u, raised to the second power, times dx, which we said is equal to du divided by 3. So if we have written the integral in this form, then easily we can evaluate the integral in terms of u cubed over 3, and therefore come up with 1/3 times u cubed over 3 plus c. But again, a reminder, if you are using a u substitution, after having evaluated the integral, you need to write back the integral in terms of the original variable. Hence, we will be replacing u now with 3x plus 1, and write now the integral as 1/9 times the cube of 3x plus 1 plus the arbitrary constant c. As a summary, to recap what we have taken up in this lesson, that integration is just the inverse process of differentiation, and that the basic integration principles are also the inverse of the basic principles for differentiation. That evaluating integrals involving powers of some expressions in x or in any independent variable can be easily done using the chain rule for integration or by using the general power formula for integration.